we say not of A and B. So we can define not by two method. One is this complement, the other way of expressing not is this one. So let's try to write this as a statement first. So not of A, and this is for and B. Again, so we'll take some example to understand more about this. So let's say we say what is not of x is greater than 3 and x is, let's say, less than 4. So first we'll try to draw as usual on the number line this to understand it more. So we have x is greater than 3. So on the number line again, this is your 0, this is your 1, this is 2, this is 3, and this is 4. So when we say x is greater than 3, meaning by this, and when we say x is less than 4, meaning by this, right? Now if you see the combination and, so this needs to be together. So this is the part we are more interested. So this expression means what is not of. So we say not of x is obviously greater than 3 and less than 4, right? So this is the part where x is greater than 3 and x is less than 4. So if you look at the not of it, you will find that in this number line, this part and this part, these two parts will be the not of this expression, right? So we can write that not of this is equal to x is less than 3 or x is greater than 4. So how do we arrive here? You can see that it's obvious that the not of this is this part, right? Now how do we arrive here? So there is a lemma or the theory behind it which will be helpful for you to understand all these things. So let's try to go into that theory first. Okay. So we have established through the number line that not of x greater than 3 or and x less than 4 is equal to x less than 3 or x greater than 4. Now if you look closely, this one is not of this one and this x greater than 4 is not of this one, right? So we can clearly say this four is not of x greater than 3 or not of x less than 4, right? Or you can say that given, so we have established here that this not of all this expression is not of this statement, and here and is replaced by or, right? So you can simply write this expression. If there are two expressions, we can write not of A and B is equal to not A or, so we can write this like or not B. Right. Similarly, if you look at the other expressions like not of A or B is equivalent to not of A and not of B. So you see here, when you put a not here, the and expression changes to or and the or expression changes to and with the two nots there. So let's try to find what is the not of there exist. So we'll write the similar statement for there exist and for all x. I'll not explain this, but just for I'm going to write this so that you remember this. Again, for not of there exist x such that A is the statement out here is equivalent to, for all x this is for not of for all x there exists an statement A. This is equivalent to there exist x such that not of A. Similarly, not of there exist x with statement A is equivalent to for all x there exist not of A. So I'll write all these things in one place so that you will okay. And I also want to discuss one more thing which is also used very often is this expression. So what is, let's say A is an statement. For example, x is greater than 3 or greater than equal to 3. So again in the number line it is 1, 2, 3. So you can see that this part is with a closed one because we have equal to sign here, is x is greater than 3. So what is the not of this one will be this part with this open, right? So this will be represented as x is less than 3. Now what if we find the not of this not, right? So if you look at it, then it will go again like this way, which will be again, so if we put not of here, then it will be, you know, x is greater than equal to 3. So now I will write all these statements so that you can remember it at one place. The first one we have will be the easiest one. The first one will be yes. So the not of, say not of theta is a statement this time, is theta. Secondly, we have established not of B and C is equivalent to not of B. Okay, sorry, I have written both the things, or not of C. Similarly, we have established not of B or C is not of B and not of C. Then we have also established that not of there exist x such that A is equal to not there for all x there exist not A, right? Similarly, we have also established not of for all x there exists a statement A is equivalent to there exists a statement x such that there exist not A, right? So all these things are quite important, and as we move to our next part, which is the basic set theory, you will understand more about how this is used in mathematics and why I try to explain all these things in so detail, because this will form the foundation of your counting, the probability and the set theory. So in this session I also want to discuss about the various method of proofs. So I'll not be discussing all the methods of the proof, but I'll be discussing here the two methods of proof. So the first one is by proof by contradiction. So I'll just give you an example here. I am not going to prove the statement. So proof of contradiction is that if some statement is true, right? So if you want to prove something, then you find the not of that and reach at the ambiguity that this cannot happen, hence that statement is to be true. So let's take an example. If we want to prove that root 2 is irrational, so what we will do here is we will assume that root 2 is rational. So if we represent this as A, so this will be A not A, right? Because if root 2 is not irrational, then it needs to be rational, right? Now if we reach to some ambiguity or contradiction that this is not possible, for example, if we reach by this is 1 is equal to 0, so we know that this is not possible, right? So meaning by this not of A is not possible, so A is possible, and we prove this by this method. So this is called the proof of contradiction, right? I'll give you another proof, a method of proof which is quietly used in mathematics. This is very important. This is called proof by induction. So this says that given for any n, so it always talks about the natural number, so it says for all n, if an holds, an is true, this implies for n plus 1, n plus 1 should be true. It also says that a1 should be true, should also hold. Now what does this hold mean? So let's take an example. If we have to find the sum of the first successive n numbers, so this will be 1 plus 2 plus 3 plus n, and we say that we know that this is equal to this. Now how we are going to prove this? Okay, so in order to prove this, first we find, so our expression here an is this part, so which is, we can write it also like that, n, right? Now if you find a1, we know that sum of this will be only 1, so if you put the value 1 here, it will be 1 into 2 divided by 2, so we see that this is correct, right? Now we assume that for an, so we assume here now that for an is equal to n into n plus 1 by 2. Now we need to prove that for n is equal to 1, n plus 1, sorry, n plus 1 is equal to n into, this will be n plus 1 into n plus 2 by 2. If we are able to prove that, we will say that for any n this will hold true, and this is called the proof by induction. These are the two methods of proof which will be used in our counting and the probability theory. It might not be needed very frequently, but it is good to know all these proofs, right? So with all this, I sum up this series and we will move to our next series, which will be the basic of set theory. Thank you.